Today I want to talk about sample size, and it's, as many of you know, it's the most common question you'll probably hear once anybody finds out that you understand anything at all about statistics. If you even just mention that you are doing a hypothesis test, for the next 3 years people will ask you to help them sort out how many samples they need. The most common question I get when working with projects and product development early on is, well, how many samples do you need for the reliability work? And I usually say something like 8,000 or 9,000, and which would be great if we ever got that many. Oftentimes, that's a non-starter. Some organizations, some places, we may get one and then ask not to break it. All right. Well, what do you do? What's important? How do we frame that and deal with that? And I'm curious, what kind of responses have you gotten when you say, hey, we need lots and lots of samples? What kind of pushback do you get? I know that I've had laughter. I've had, are you crazy? That's not possible. No way, not possible. Yeah, perfect, Mark. Yeah. The part of what it is we need to consider and we need to make sure is clear, it's not just a number. Like we could say 77 samples from 3 different batches, which is common in some standards, or we could say 30 samples, or we could say 3 samples, or we could say whatever number the math comes out to, yet it may be enough or not enough depending on what we're trying to use the results for. You know, if we're deciding a simple thing, then it's no big deal if you use whatever. If it's a critical business survival type decision worth tens of millions of dollars, well then let's do the due diligence and get enough samples to make a good decision. Yeah, and Dennis, you're right. Others will come after you for time and so on. So we're under a lot of pressure, especially for longer lasting testing that we do in some cases, that we don't even have prototypes yet. And we're trying to design and get samples to run a 6-month test, for example. And sometimes that's a big consideration, is you just physically can't get samples. But the bottom line is that we don't need samples just to run tests. That's not the point. We need samples to run experiments and run tests that gives us information about the population. And it's a decision. Is it ship or not ship? Is it change or not change? Is it vendor A or vendor B? And we'll talk more about that as we go. And then there's constraints, and we've already alluded to that, right? We're only going to make 10 of these ever, these big systems. A medical product I work with was kind of like that. And it was a huge, expensive piece of equipment. There's only a few places in the world that are even potential customers. They expected to make 10. And asking them for 30 samples of their entire system was just not going to happen. And so there was a real constraint on that. And there's money constraints and time constraints and on and on and on. And we'll get more and more into the constraints that we face when trying to procure samples, and then what we can do about that, options we have. And so those are kind of a quick overview of what I want to get into this for. But here's, when you get that question, how many samples do I need? And then we say way more than you want to do or use or commit to. What are the ways that we commonly use samples? And I mentioned life testing already, but why do we want samples to start with? Why can't we just test everything, for example? And hello, Iknor, and all the others that could join us today. It looks like we didn't lose too many from last week, so I'm glad that it worked out for everybody's schedule. Still got a few people coming in, but I like starting on time, if you haven't noticed, or as close to on time as I can. So why do we use samples? What's the reason we do that? Yeah, we don't have that's a good point, Mark. I hadn't thought of that. We don't have enough test facilities, enough chambers, enough hookups, whatever, to actually test everything. So it's just physically, we don't have the facilities to do it. Yeah, yeah, good one, Bob. I had my boss one time says it's really tough to sell destroyed products if we're going to 100% do destructive testing. And he says, well, it gets us the best data. If we really want to know what's going on with our product, and we have to test them all and happen to be a destructive test, it becomes a trade-off, right? And then confidence, cost, and test time. Those are all elements of it. Um, Sometimes we get enough information from a small sample in the given circumstances and constraints we have to go forward. And sometimes we don't. And I think part of this question is what's the appropriate sample size to use for making a reasonable decision? Now, there's going to be a risk from using a sample, that the sample won't represent the population. And more samples is better at making sure that is minimized, that confidence in type 1, type 2 error is minimized. Yet, keep in mind that we're using samples to represent a population, and there's risk involved there. And we're using that to make a decision. So if somebody says, how many samples do you need? And you say, I need 10 samples, and they say, no way. He says, the follow-up question is, what decision are you going to make based on the testing or experiment that we're going to run? And 10 samples may be too many, or it may be too few, unless you understand the context of what you're using those samples for. And so we'll talk about a number of these different elements and constraints as we go into it. So a little more detail on kind of my thoughts on why we sample. Yeah, and Christine, good idea we'll talk about how to get around sample size costs and stuff like that, and components and coupons and material sets is a good way to do it, and it's not the only one though. But why do we sample? And there's a couple of different reasons on this thing. And as I was setting up the presentation, I was hungry, I think. So I'm using a chocolate theme basically for this one. But there's a lot of samples or units out there in a population, and it's really just a statistics terminology thing. The sample is a slice or a subset or a portion of a population, and a population is all of them, right? If you want to measure the height of people in your country, you could run around and measure all of them, or you could take a sample, and there's all kinds of techniques and rules and benefits to doing random samples and doing it well versus not. But the idea is that it just may not be feasible to measure the height of everybody on a particular day. It just not enough resources, not enough tape measures, maybe, whatever the rule is. And so using a sample may be good enough to give us an idea of the population characteristics. And so cost, test time, all these other things that we do, but also sometimes we just need to know, is there enough sugar in this donut or in the frosting? And a simple taste would be good enough. The variability from the amount of frosting in the batch that was used, you might only need to sample one per batch to understand if the formula was executed correctly and you got enough sugar in it. Which reminds me, I did cook once where it was a bit more salt than expected and a lot less sugar than expected. Somehow those two got confused. And the frosting was really bad, and on the first taste, we found out. So feasibility is a piece of it. And another piece here is that sometimes all of your population hasn't even been created yet. right? So if you're in a development project and you've got prototypes and you're trying to make decisions about the eventual production you're going to do, well, that's still in the future. You haven't gotten there yet. So we're not even able to do a random sample from the whole population because it doesn't exist. So another piece, a question I'm seeing come up here, or a note, um, yep, sample size, depend on failure mechanism. You know, if I believe so. If I'm going to be sampling, I don't know failure mechanism, but it would be um, the failure rate. If I have 100 pieces of pastry on the table, and the failure I'm looking for would be that salt that would be accidentally too much on all of them, then I'd only have to sample one. But if the failure is that one of the batches of all these different confections was one of, say, maybe only present going to be, or only going to be present in a small fraction of them, right? Well, then I need to sample more to find out, is that small fraction present or not? So if you have a very rare failure mechanism, or it's a batch-related failure mechanism, you have many batches, and you don't know which one it is, then that will dictate some of those sample size considerations and sampling type considerations. Yeah. Yeah. Another part, and it was mentioned, I think Mark mentioned it, is if you're doing destructive testing, you really are forced into doing a sample of your production. It's hard to sell stuff that it's not there anymore. And then cost. This is the most common one that we get pushback on, and especially, excuse me, in product development, where prototypes are amazingly expensive in many cases. And so, and it's not just the sample cost, the cost of the samples or the prototypes we're trying to go. Sometimes our testing is very expensive, or how we make the measurements, or the analysis, if we have to do a detailed chemical analysis on every sample. The cost of executing the experiment and how many samples you have becomes part of those constraints, and is part of what we can do. And yeah, Dennis, physics of failure and modeling can help. Understanding your failure mechanism is, I think, part of that process of figuring out your sampling scheme and sample size, but also in estimating the cost. So if you have a failure mechanism that has a degradation type behavior, and you can measure that degradation and sense it before it fails, you save time, you could use less samples, there's all kinds of elements there that become a benefit to you. Whereas if the sample size, or if the failure mechanisms is rare and gives you no precursors to that it exists, it's harder to do. It may cost more to actually run the experiment and find those rare events. So lots of constraints, lots of reasons that we use samples versus not using samples. Now here's one for the statisticians in the group. I often call it the magic numbers of sampling. And we learned it in college statistics classes when learning about the normal distribution. They often say a sample of 30 is kind of the magic number to give you a reasonable estimate of the normal distribution's parameters. Later I learned about, I think 22 was another standard sample size. Does anybody remember what that's for? Or 77, what's that standard sample size? Where'd that come from, and why is that a magic number? Or do you know of any other of these magic numbers, or your go-to sample sizes? Six-pack test. I've heard of that. Bob, I'm not real familiar with that. Is that 6 samples from a group, and what would be the purpose of that type of approach? Don't be shy. I'm not going to ask a question on every one of them. B to C test. Okay, I'll have to dig into that. 45 samples. I haven't heard that. 11, 29, 59. from the binomial. Yeah. Might be 95, 95, 90, 90. What's the 11 samples? Is that like 80, 80? 80% confidence? Yeah, Thomas, as often is, yeah, it's one more sample than you have. You need one more sample than you have available. That often happens. Yeah, and doing comparisons, that works great. Yeah, 30 for the normal distribution. Um, Anybody know where 22 samples come from? Where's that? Yep, 90-90 for a binomial distribution. Yep. One of the things, and it's one to keep in mind, is that when you do a pass-fail style test and you're using the binomial or a similar distribution, um, if you can switch that to measuring a characteristic, instead of just pass-fail, it's in spec or out of spec, is, well, where is it? What is the actual voltage reading, for example? And use the continuous data sets when you can and get out of the binomial. Oftentimes that gives us an advantage for the same risk profile, essentially, the sampling error. That gives us an advantage and reduces sample size. And we'll talk about some of these other constraints. Yeah. All right. So one of the things, oh, and I should mention on that standards type stuff, if I've seen all too many times where somebody opens up a standard and they say, oh, we need 22 samples or 29 samples or whatever samples. And the standards often don't detail what is the sampling risk and what you can and can't conclude from those results. My favorites are when they say take 3 samples. And if you work out the math on that, other than doing a halt test and running it to failure, which oftentimes standards don't do for standard style testing, they take 3 samples, run them in a chamber, and if they still work, you're good. Well, not so quick. There's lots of problems with that. I think we need to do the due diligence to understand the risks that we're facing with a given sample size so that it can inform the decisions that we're making. And I don't believe the standards, the sample sizes and standards serve us and our decision makers. They are a starting point. They're a way to think about it, but I think they sell us short and way too many times. All right. So a couple of things just from the statistics side of things that we need to consider, and then we'll talk about some of the business considerations. All right. If the population variance, the variability of the things that we're sampling, if they're very, very consistent, and we're looking for a difference in our test, say a simple hypothesis test, then we won't need as many samples to detect, say, a 2 sigma shift. It's one of those, think of a control chart, right? We're taking samples, and if we get something outside the control limits, we really only need that one next round of samples to detect that if the process has shifted that much. If the variability is very tight, we can detect finer shifts in the mean easier, which means fewer samples. And I'll show you one of the formulas of where that fits into it. But oftentimes we're given the variability of our population, or we don't even have the population yet to get an estimate of the variance or the standard deviation. And it is a major factor in how many samples we need. And it's one of the things that we're often forced to make some assumptions and essentially guess at this one variable, which really does, to a significant degree, dictate how many samples you really need. And so it's one of 3 different things from the statistics we need to consider. And if you are in a corner and you really need to reduce your sample size, well, your best effort may be reducing the variability. Get your population, the process that's creating the samples for you, under control and very tight. And that serves not only to get fewer samples, which is everybody will like, it also helps us to create a better product. it has less variability in it, oftentimes translates into a higher quality product and a more durable or reliable product. Yeah, and Mark, you mentioned the power function. It's part of it, right? I think it's the next, no, it's the third consideration in statistics, the power and the confidence, those kinds of things. And maybe you're answering another question here. But let me see, I saw one from Murray. Yeah. Um, yeah, and Murray, one of the things I'm going after is that there's a statistics part that tells us what to do, and these variability, discrimination, and confidence are parts of those considerations. And then it's balance that with the business needs, and we'll get into those in a moment. And it goes back and forth. It has to be a balance. Discrimination, I don't know what the right term is for this. It's often that term in the sample size calculation that I explain as it's the difference that matters. So if I'm looking for sugar content in these different images here, and I'm doing a chemical test, do I need to know down to the gram or very a tenth of a percent of overall volume by sugar, or is it a grosser measure makes a difference? Is there sugar or not, for example? Is much easier to detect with fewer samples if I'm looking for a big change. But if there's just sugar or not sugar, that may not be what I'm trying to get. I may need a particular ratio by volume of sugar in this recipe in order for it to work, and I want to test that. Well, if I need, I'm going to make up numbers here, 10% of volume is what we're interested in. Well, what's my tolerance? When is too little sugar important? Is it 8% or 5%? Or too much? Is it 12% or 15%? And the closer I am, the tighter that range of interest is, that difference that I'm trying to detect, I'm going to need more samples, right? In order for any given standard deviation, I'm going to need more samples to detect a smaller change, because the samples themselves provide some noise and some variability. In order to detect the difference between what is a real change or difference versus what is just noise in the sampling, then I need more samples to overcome that problem. So part of the business decision is, well, do I need a 2% tolerance, or is 5% good enough for us to make a decision? And that's where keeping in mind what you're trying to decide and what's the important criteria for that decision then can inform, well, what kind of difference I'm trying to detect or discrimination I'm trying to sense. How precise do I need to be in detecting a change? And it's a statistics problem. And so obviously if your population is very small variance, we can detect smaller changes very easily, or easier, I should say. Whereas if the population is very spread out, has very large variance terms comparatively, in order to detect the same difference, I'm going to need more samples to determine if it's really there or not. And the third one is one that we all wrapped our brains around at one time or another, is the sampling error. Now, type 1 error is often called out, and it's part of so many formulas. There's two types, and I think Mark or somebody mentioned it earlier, is the power function, which is the 1 minus the type 2 error. And these are the errors that account for the random sample that we collect, assuming that it's random, from the entire population, which we often are not able to do. It provides us, there's a finite chance that the sample itself will lead us to the wrong decision from what is actually happening in our population. Right? And it's just sampling error. It's just, there is a chance that we pull everything from the right tail, and everything looks, then the results will be maybe a higher mean value and a smaller variance. Now, the likelihood of taking some number of samples all from a very tight range in the upper tail of any distribution is exceedingly small. Yet, it's finite, and it can happen. And the hard part is at the end of the day, we don't know, was our sample a rare occurrence where we got values that mislead us into where we think the parameters are. And so we go through the exercise of considering, well, how much error can we accept for the decision we're doing? In some organizations I've worked with, and a couple just recently, is they set up a table basically saying if it's and this was in a medical device, if it's a life-threatening or serious harm to a patient issue, we do 99 confidence is what they raised it at. And that forced them to generally have way more samples for work they were doing that was related to that mechanism, that failure mechanism. Whereas other things that were nuisance problems would be at 60% confidence. It wasn't that critical to the overall performance of the product. And it doesn't have to be just safety, it could be whatever you decide is important or not important. And I was teaching a class years ago in Korea, and we're in this part talking about sampling and sampling error, and I asked, well, what would you like your test to be run at? How much error can you accept from this type of problem? And the director was like, none. We really want 99% confidence or 99.5% confidence. I'm like, wow. You know, that may mean a lot of samples. And we went down the exercise and we got some real data, and their variance of their units were so small, they were so identical from one unit to the next, that we only needed 3 samples in order to detect a change that would impact the performance of the product. So confidence is a business decision oftentimes, and it's based on the finite probability that your sample will be misleading. And we don't know at the end of the day. So it's a confidence, variance, or variability, and discrimination are 3 of the statistics related decisions that you'll see elements of in the formulas. So let's say somebody says, well, let's just reduce the confidence, right? We'll do a type 1 confidence and cut it all the way down to 50%. And I've seen this in standards too. I've also had a boss tell me that he said, well, we could cut the samples even further. Let's use a 25% confidence, right? And I'm like, do we really want to do that? How would you explain it to somebody that you just can't reduce the confidence and take on more risk to reduce sample sizes? Now think of what it is, right? This type 1 sampling error, this type 1 confidence, or this type 1 error, alpha confidence that we commonly see. It is the chance that our sample will give us an answer that's not within a particular confidence interval or range. It says that our value that we're looking at the end of the calculations and end of our readings and samples and measurements and whatever is representative or not representative of the actual population. Yeah, so Christine, you get a 50-50 chance that the data that you end up at the end of the day represents the population, and 50% chance it doesn't. And you don't know which way it is. Yet there are standards out there that advise you to use a 50% confidence. And at that point, save your money, don't use any samples, and just flip a coin, because your decision is based on pretty much a 50-50 shot. Now, if I'm flipping a coin, to see who pays the check at lunch, well, then it's 50-50 and we understand the odds, and that's great. But if I'm trying to make a decision of vendor A versus vendor B, and it makes a performance issue difference in our product, do I want to just leave it to chance, 50-50? And if I do a 25% confidence, that pretty much guarantees that my answer is going to be outside where I think it is, where the results tell me it is, most of the time. But we don't know above or below or if it's inside. We just don't know. You know, and years ago, I was talking to a statistician at a campus and asked, well, where did 90% confidence come from? Where did these old things come from? And it apparently goes all the way back to Fisher, and he goes, well, that seemed reasonable. There's no hard and fast rule to what risk you're willing to take. But if I'm running an experiment and there's a huge investment in it, understanding those trade-offs makes sense. Is if you reduce confidence, you reduce sample size at a cost, at a price that the answers themselves will be not terribly useful. Yeah, 85 or 87 or 93 or 92.6, they're all arbitrary, yet they are related to a finite risk that your sample results will be misrepresentative. They just won't. They'll give you an answer that will lead you to make a poor decision. And so our inclination is to have little or no risk, and then you see the sample size explode and go through the roof, and then you go, well, we're going to have to accept some risk for this decision, and it becomes a trade-off with what we're going to talk about next, the business considerations. And this is, I should have put this first, it's really where we should start our sample size decisions and what we want to, in order to do the calculations and come up with a number, we need to understand to a large extent these business considerations. The one is cost or availability. Is it even possible to get samples? So if I'm setting up an accelerated life test and I don't have a good model yet, I know I need to create a model, and I open up the textbook and I'm going to need like on the order of 80 to 100 samples to do what we're trying to do as a first pass looking through this thing. Now, if each sample costs me $10 million and that completely destroys any hope of profit from this product line, it's pretty unlikely I'm going to get those samples to run this test. So at that point, stop trying to do the accelerated life test and go figure out something else to do. And I saw some of the discussion talking about doing HALT, highly accelerated life tests, where you do 1 or 2 samples, some argue for 4 systems, and run them to failure. Apply stress in various ways to cause failures to occur. You, of course, can do this on subsystems and on components and materials too. But the cost is often known, or the availability is known early in programs, or is at least estimated, and it can balance what's feasible or what's reasonable to ask for. Now, there is the old way of doing it, the old school way of doing it is always ask for twice as many samples as you need. But I think many program managers have figured this out, and they automatically cut it in half and then cut it in half again. So your mileage may vary on that approach. Yeah, and Dennis, you're right. If we have too few samples, right, it turns on, but it doesn't relate to will they all turn on when we're doing in the population. If it's too small, we may miss the ability to detect, say, 40% of the population is dead on arrival. If we only test 3 samples, we may have inadvertently picked just 3 of them that worked. Very, very likely. Where if we tested 30 samples, the chance of a 40% defect rate going through would be very small, and we would detect that. So it ties into this, how important is this decision? Right? So if we're going to make a decision that guides the functionality of our product or the design or suitability for a particular environment, something that every product would fail and it would cost us tons of money in warranty and lost business and all those other things, well, we may need to understand that we're going to need more samples for the important critical decisions. Now, of course, it's going to vary depending on what's the mechanism, what are we looking for, what's the rate of failure or the consequences of making the bad decision, and so on. So if the end of the day, our new design has to be 95% reliable at 2 years. That's our goal, and we need to show that and understand and make sure that that actually happens. And that may be a go, no-go decision for a product line. And it may be millions of dollars of investment to make that happen. And so that decision is going to require more samples in order to help you refine the results such that it's clear it's either 95% reliable at 2 years or it's not. And parts of the cost, the discrimination, do we need to know it's 95.1% reliable or better, or is 95%, if we're at 90%, are we okay and we'd still ship? Is there a tolerance around that number that we're close enough? And usually I go into those discussions, well, if all of them fail immediately, we know we don't want to ship this thing. Well, that's 100% failure rate. That's easy to detect, we hope. Is 50% defect rate too many? And most people say, yes, that's too many. I have exceptions to that I've run into over time. They're still not in business. They're not in business anymore. Another group said, well, this is our first product. We're doing a limited release. If 80% work and meet our goals, that's good enough. We'd like it to be at 95% reliable, but if we get 80% to start, and we know we're going to continue to improve and update our products and so on, and we can continue to run tests and so on to get a more accurate result, that helps us say, well, here's the decision point. 80% reliable at 2 years is much easier to test for, sample size-wise, than 95% confidence. And so how important is the decision? What's the balance point of how good is good enough in order to make a good decision? And so it's an interesting way to balance how many samples you use. And then what's the purpose, right? If we're just doing a halt test, I shouldn't say just, but we're running a halt test and we're running to find failures that would affect all of our products, a couple of samples is all we really need. And then it's more thought and engineering into, well, how do I examine it? How do I evaluate it? How do I stress it so that we get meaningful results? The cost there comes into the failure analysis oftentimes, rather than the testing itself. If the purpose is to distinguish, is this a 90% reliable or is this 95% reliable between, and we've made enough improvement to justify the change in the design, that's a tighter discrimination. And it may be a more complicated test and so on. So if the purpose is a clear question that we're trying to answer, the likelihood of finding the right sample size is up tremendously. So if somebody comes into your office and says, hey, can you run this life test for me? Go figure out the sample size. Your first question would be, well, what are you going to use the results for? Okay? And if it's, oh, we just do it all the time, nobody ever looks at it, well then why bother spending all those time and resources to run that test? Just don't do it. Tell them save your time and money, and you're going to ignore the results anyway, so don't bother. If it's a critical decision, and the purpose is to inform that decision on April 3rd of next year, well, now I have a timeline, I have the business priority, I can start talking about budget. What hangs in the balance with this decision? Is it tens of dollars or tens of millions of dollars? And that starts to frame a budget for actually doing the experiment, how many samples you can get, and so on. So think through what are you going to use the decision for? And how is that decision going to impact the business or your customer? Why is that important? And those elements then help you frame the constraints, essentially, and the arguments for balancing resources out there. And you may end up still coming in with twice as many samples as they're willing to pay for, but that then goes back to your understanding of what did the purpose change, the importance of the decision change, the business dynamics here change something. Why are we willing to take more risk to reduce the sample size when this is a critical decision? Or did we misunderstand that? And so on. So you often have those kinds of discussions. So quick quiz for you. Can a sample have no risk? And this is not really intended to be a trick question. Yeah, no, Christine, what do you mean by zero samples? No samples will be no risk? Yeah, if you don't sample, okay, interesting. Yeah, that's a way to do it. I call that the Dilbert approach, or the Dogbert approach, is this, yeah. If we're going to use a sample to represent a population, just on pure statistics, unless you're measuring every single one of them and have no measurement error, right, then you've got perfect data. Well, we have measurement error that exists, and we often are using a sample which has its own sampling errors. And so there is a finite, statistically calculable risk that our end of the day results are not going to represent the population. Now that's important when it's an important decision. We just need to know if the green light shows up and it's kind of green and we don't care which shade of green it is, we might only need one sample. If we're interested in the variability of that shade of green light and it has to be within a very tight tolerance, then we're going to need more samples in order to estimate the variance, for example. There are ways to get enough information to make a decision. In my opinion, any of those, what we're doing when we're calculating sample size is understanding that there is a risk and we're trying to quantify that so that it can be balanced and understood as we make the decisions. All right, so let's take a look at a sample size formula. So here's one, and many of you, I'm sure, have seen this in one textbook or another, or have used it in one form or another, is comparing means in a hypothesis test. We're going to say the null hypothesis is the two means or averages are the same, and the alternate hypothesis is the new sample is different than the population. The sample is different than the population, or different than what we've done before. And so if you take the hypothesis formula or confidence interval formulas and you can solve for sample size, you get something that looks like this. It may not have both the type 1 error, the alpha. This is the standard normal z sub alpha would be the type 1 error, and it's 1 minus the confidence is what alpha equals. And beta here, the z sub beta is the type 2 error. And 1 minus beta is the power. It's related to some extent, the discrimination of the task, but also just the sampling errors that could exist there. But notice this. If the variance is high, we need more samples, right? If I increase this value just a little bit, it goes up by a square, where it's just the whole variance term, sigma squared. It's the variance. As that goes up, as the variance goes up, the sample size goes up proportionately. With everything else constant, it just goes up linearly. If we often think of standard deviation, then it goes up by the square of that. A change in standard deviation, then sample size goes up in weird fashion. The confidence is very much the same. If we go to higher confidences, this alpha term gets smaller and these numbers get smaller. We need fewer samples to a squared on a squared function. If we go, if we want higher confidence, these numbers get bigger, and then it goes up by squared, and we need many more samples. For 90% confidence, we need, say, 22 samples. For 95% confidence, we're going to need closer to 75 samples. I think it's 79, if I remember right. And then it just gets 99, it goes up even quicker. You're into hundreds of samples. So more confidence, higher confidence that your sampling error is minimized, then you're going to need more samples. And this delta here is the discrimination. So if I make the discrimination large, I can go plus or minus 10% versus 1%. I need many fewer samples. Try to pick the right English word here before my English teacher rolls her eyes again. If I can tolerate a wide difference is what I need to detect, this delta squared goes down, and I'm dividing that smaller number into everything else, and I can detect that with smaller samples. So, yeah, a good point, Mark. And some of the software packages we have these three different terms. You can play with those and experiment how they work. I just use Excel. It works really well, and it's a balance. But this is a complete, has all three elements from the statistics point of view. And then you can say, well, if I need 22 samples, it's going to cost me $50,000. If I need 11 samples, it's going to cost me $25,000, or whatever your cost per test is, or whatever it is you're doing, and what's the balance. And then what do I change, right? I can look for a bigger change if that makes sense to support the decision. I could use less or increase the risk of sampling error to a point. I recommend 60%, nothing less. So you only can go so far with that, and you can get some advantage. And sometimes the variance is just going to be whatever the variance is, and we have no control over that. If you can reduce the variance of the population, not of just your sample, we'll be able to go with fewer samples. And it's the first thing I mentioned is oftentimes we're assuming the variance, which is hazardous, in my opinion. We need to really get a good number for that as a way to hone in what sample size we really need and what risk it presents. So success testing, and I think we mentioned earlier the binomial testing and the 22 samples. And so this formula is the natural log of 1 minus the confidence. So if I want a 90% confidence, and it's really the type 1 error that we're dealing with, this would be a 0.1, natural log of 0.1. The natural log, in here I'm using reliability as the lower bound of our reliability. So let's say we want to be at least, our tests give us results that we're at least 90% reliable. Well, I put in 0.9 in this R sub L term here. And if the test we're doing is replicating one lifetime, one span that we consider a lifetime, it might be your warranty period or expected life or useful life or whatever period you define as a lifetime, M would go to 1. And so that's natural log of 0.1 divided by natural log of 0.9 equals 21 point something, and you round it off to the next whole integer for 22 samples. Therefore, if we run 22 samples and for one lifetime and all pass, that's why it's called success testing, then we can conclude that we're at least 90% reliable with a 90% confidence. Now the advantage is if you run the test longer, you're able to run for 2 lifetimes, you cut the samples in half. Right? Now, the longer you run the test, in multiples of lifetimes, the more likely you are to bring on failure mechanisms that aren't relevant to a single lifetime. But those failures still count across this test, and so there's a limit there of how many lifetimes I recommend you can do. You're limited by confidence, by the 50%, I'd say, or 60% would be it, and then it's a business decision. Well, how reliable do you want to detect it? Right? Now this one doesn't have, it has confidence and it has reliability, but it doesn't have the variability part specifically in it. because it's a pass-fail test. And here we're designing and running a test that if they all pass, the test passes. If one fails, this formula doesn't work anymore. We have to go back to the textbook and open up the binomial with some failures in it. And then our confidence and or the reliability we're able to demonstrate, for example, is much, much less. So it's a hazardous test to run for lots of different reasons, but it is, for a pass-fail style test, it's the most economical. I highly recommend using time to failure type testing, much better there. So M is the number of lifetimes. So if, let's say I'm running a test and I want to know if it's 90% reliable over 2 years of duration. And I have a test that would replicate 2 years. It might actually be 2 years testing, or it may be an accelerated test that gives me, is it working after 2 years of stress or abuse, or think of a hinge, a car door. How many times does a car door going to be used over 2 years? And there may be a specification for that. So if I run 10,000 cycles on this car door, which represents 2 years of use, M would be 1. If I do 20,000 cycles, that would M would now represent 2 lifetimes, and it would be the number 2. So it's, hopefully that makes sense. Okay. So I think I have one other one, a bit more complicated. This is from Bill Meeker and out of Meeker and Escobar's book, and it has the various terms in it that we're interested in. Get my little green guy here. Here's the confidence, right? Still a squared term. Here's the variance, and they have some adaptation to the variance terms of what you're looking at, and the book explains it has all these tables and formulas for adjusting the variance terms of measurements you make to be suitable for this accelerated life test design using a Weibull distribution. And it has the reliability term. And again, it's squared. So variance is standard deviation squared, reliability squared, and confidence squared. Same phenomena structure statistically as the hypothesis test type thing. And here is an interesting phenomena. These numbers, each line represents the expected number or expected proportion of failures you expect in your test. So if you're expecting a very rare event, and or you're just not running the test very long, and you're expecting a very small number of failures, you need many more samples than if you're up here closer to 40, 50% of your samples are going to fail. You can get by with many fewer samples. And then also the quartile of interest is, well, are you looking at the early tail of your life distribution? So you want to know when the first 1 out of 1,000 fails, or are you interested in when the first 10% fail? And so the further up that tail I'm interested in, say 5% or 10%, I can get by with fewer samples than if I'm looking at the 1,000th percentile. And so it's considerations like that, and Bill and Lewis did a nice job creating these graphs that help us get these concepts across. And the only real complicated part to their formula is estimating the variance and adjusting the variance because of the time nature of data. And one of the assumptions is that the variance over time stays relatively constant. And again, that's not always true, but it's worth understanding how that impacts your decisions. All right. So what are some of the best ways, we got a few minutes left, to reduce sample size? Well, one is don't do testing, right? Use previous models, use field data from in the past, use engineering judgment. More and more, I'm learning that doing testing is really a last resort. Yeah, we like to break things, we like to put stuff in chambers and like to run stuff. But if at the end of the day, those results really don't help us make better decisions, if we're only using 1 or 2 samples per test and we got 15 tests running, we're probably really not learning anything. We may find some failure mechanisms inadvertently doing halt, yet we're not able to estimate the failure rate for some of these things. We're still going to rely on modeling and other work to do it. I'd much rather focus on the areas of the highest risk and unknowns to our program. What are the most important decisions? And put your samples there. Get a better result, and that you can really make a decision. And use HALT to find and ferret out the unknown failure mechanisms. And again, it doesn't take a ton of samplings. But modeling, simulations, history, engineering judgment really do help you reduce sample size the quickest, I think. Any other ideas? How do you, and I guess the contrary question or complementary question to this is, how do you get enough samples? Yeah, sequential sampling, that's a good one, especially if you're really limited to doing pass-fail type testing. Sequential sampling is actually pretty decent at minimizing the number of samples you have. Better than sequential sampling is measure a continuous variable or measure a degradation pattern. So if you can, especially life testing, if I can measure the degradation and model its path time to failure, I get 100% failures then, and I can really minimize the number of samples I have. I don't have to censor heavily in my accelerated testing, and I get a more accurate time to failure estimate, and I can do that through degradation measurement and tracking out to failure. Yeah, understand the mechanisms, and sometimes it's getting around the constraints of cost, and especially of complex systems, is hone in on the specific subsystem or component or material set. And that may be plentiful and allows you to get enough samples. Now, of course, there's risk. Does my subset behave in a similar way towards its failure as it does when it's in the larger system? So some due diligence and engineering is involved there to make sure that it works. Yeah, so I think we've got a few ideas there. Good, thanks, Christine. Sayed, Jason. Yeah, Jason. I'm a frequentist by training, and the Bayesian guys were across the Bay Area here from us over in Berkeley, and our football teams didn't like each other. So somehow along the line, I didn't really grasp Bayesian statistics. Now, the few times I've actually cracked the book and worked on it and saw the Bayesian modeling and doing priors and all kinds of cool stuff that it can do, the end of the day is it saves me one sample. So instead of 22 samples, I only needed 21 samples. Now that may be the difference that makes a difference, and you squeeze as much information out of your samples as possible. So I'm not saying it's a bad idea. I just found it way harder to explain, and part of that is I don't fully understand it myself. So I tend to stay with like sequential sampling in the classical, in the frequentist way, whereas there's a Bayesian approach to sequential sampling, but at the end of the day, it saved me one sample. And so it didn't really make a huge difference. And there was one that my client then could understand without a degree from Berkeley in statistics, so they were happy to add the one more sample. So, of course, your mileage may differ, and hopefully you understand it better than I do and can explain it clearly. That's probably where I fell down on it. So we'll wrap up a minute or so over, apologize, and what we do in our work oftentimes involves samples. But more importantly is we start with a question. Will this last long enough? Is this strong enough? Is vendor A more durable than vendor B? Those kinds of questions. In understanding the question first and what experiment or test or evaluation we need to conduct in order to answer that question, to give good enough information so that we get a good answer, is really what we need to do first before you start calculating sample size. And then it's do the data, do the analysis, go do the experiments, fit and plot it, analyze it, use the data that you have available, get the sample size questions, right? It's going to be a balance with your business requirements and needs and what's possible versus what's necessary, and try to tread that line that you get good information from your sample. At some point, it's not worth running the test. The sample will give you meaningless results, or at best vague results. So I think there's a threshold where you just say, no, we're not running that test. We have to change the purpose of the test at some point. And then go back and ask better questions. You know, what else can we learn from this? What's a better way of doing this? Next time we run this, let's budget for more samples, for example. Might be a good way if you want better decisions. All those kinds of things. And then just realize that I don't think I updated these from the summary comments aren't the same as what I would expect them to be. The essence, though, is the same as what I'm discussing, is focus on the decision that you need to make or the evaluation test or experiment you're doing that needs some samples. Well, what is it supporting? And how do you create the right or good enough information so that they can make the right decision more often? It's pretty much where it comes to. Yeah, and Murray, you're right. It's a little bit different approach to approaching the statistics, but it does help us in adding the prior information. And I'm using that in a lay term, not the way the Bayesians would do it. But if we know that what we're working on is always a Weibull distribution with a beta of 2, give or take a very small number, that will help us to understand how many samples we need. If we don't know what the beta value is, either we have to run some experiments to find it, or use history data to estimate it or assume it, or we leave it more open, more generous, a larger variability number, let's say a beta of 1, which would likely require us to have more samples. And so the more we know, not just from the statistics point of view, but also the more we know about the failure mechanism and how this behavior has happened in the past, how good is our measurement systems, all of those factors tie into these considerations for how many samples we need to create useful results. So good. Yeah, and Mary, if you have a good reference, I've been looking for an approachable reference for Bayesian statistics, because I need to put that on my well, not my bedside table because I'll fall asleep, which I do with any stats book, but in my corner to study. So that's the presentation. Thank you all for joining, and sorry about the push from last week. We had our audio problems last week, and I think those are solved. Hopefully that's not coming back anymore. Appreciate you all chiming in today and participating. I really do appreciate that. And let's see, I think I've got, do I have one more slide? Yeah, a little more information. We'll see you over at Ascendo Reliability, and we've got monthly webinars out through July, I think, up on the schedule, and a few other events in the works. So should all be fun. So I'm going to end the recording, but I'm going to stay online if there's any questions. And